As of this moment, I am recording. Let's see if this will work. There. Now that I'm not tethered to the board, I'm going to try this without my external mic and see how we do. All right, page 80. I will read some words to you, and if you don't need the pictures, then you don't need your book. We talked about all these last year, and in fact, we talked about a couple of them already this morning. The first type of discontinuity that this book reminds you were to have learned in pre-cal is a removable discontinuity. Okay? What is a removable discontinuity? A hole. When does it happen? What in the equation itself exists that makes a hole happen? We have a canceling factor in the denominator. That is, I have a matching factor in the numerator that I can cancel off, that I'm going to end up with 0 for that factor. That's where my hole is, right? And to figure out what the y-coordinate is, how do I do that? At the hole. Because here's what you got to think. You're not going to have your calculator every time you want to have it. It's going to get taken away from you a lot for the rest of your education. So you need to get used to thinking without it. So if I want to know where a hole in a function is, I would factor like we did on number 1 from the quiz, right? See that I have a canceling factor, which already tells me there's a hole here. But if I wanted to know specifically where the hole is, how would I determine? I know the x value, right? Because it's the 0 of that factor. Yes? Okay. But how would I figure out my y-coordinate? I would plug the x that gave me 0 into the other one, right? The one, and typically that's the one you're approaching. So I would plug that back into the remaining function, right? After I've canceled. Simple enough. You had a couple of those. I think that was on last night's homework you were working on, wasn't it, Michaela? And the trick to those is to do that. You cancel out whatever's there, and then you plug it back into what's left and see where you end up, okay? To get the other piece. But that won't make any sense unless you've looked at it. All right, the next one they list is a jump discontinuity. Have we seen jump discontinuities yet this year? Yeah. Yes, we have. In fact, if you drew the picture on the test, on the quiz, you probably saw one. I say probably because I didn't graph it. I just looked at the part I needed. Was there a jump there? Did you graph it? Okay. When does a jump occur? And it most frequently happens in what kind of function? A piecewise, okay? And when does a jump happen?
The limit from the left doesn't equal the limit.
Exactly. When the limit from the left does not equal the limit from the right. They're approaching two different numbers, so we have a jump there. All right? So then the next one is an infinite discontinuity, which I have gotten you into the verbiage of what term? Asymptote. What kind of asymptotes? Vertical asymptotes, right? So an infinite discontinuity is a vertical asymptote. Obviously not removable. The only one we didn't talk about last year, and I think I alluded to it a little bit when we got to trig, but I don't really remember for sure, is an oscillating discontinuity. Okay? You know the graph we put on the board the other day, sine of 1 over x, that went crazy in the middle and it looked really normal everywhere else? That was an oscillating discontinuity because it never gets to a point somewhere in there. Well, technically that's not an oscillating discontinuity. I should give you a simpler example. Think about sine x. All right? Why does my giving you the fact that I'm out at positive infinity tell you absolutely nothing about what sine is doing there? That's right, because I know that that function oscillates in the exact same way forever. So what my output is, it's not enough to say I'm at infinity. I have to give you a specific value to know anything about it, right? So that's why we have the oscillating discontinuity, oscillating discontinuity in the sense that it doesn't ever approach a value. Does that make sense? Because to approach a value, it has to mean that the farther out I go, the closer to that value it gets. Is everybody with me? All right, we already talked about continuous functions and continuous on an interval. So now we're going to go straight to, and I'm actually just going to erase the page 80 reference now that I've gotten you to jot it in your notes. We're going to talk about Theorem 6. If I can write. Me and my board aren't clicking yet this morning. All right, Theorem 6. And this is properties of continuous functions. That is our title. All right, so you have to have a preface to this because the theorem itself is very anticlimactic. If f and g are continuous, at x equals c, then the following combinations are continuous. And there are 5 of them. 1 is f plus g. And we played with this idea a little bit in pre-cal last year, so that when I add, in fact, we kind of talked about this, I think maybe even yesterday when we were talking about the end behavior model and that sort of thing, about why one was above the other and that sort of thing. F plus g, if f and g are both continuous, the graph itself would be somewhere above them at any given point, right? So, because obviously if I'm adding 2 numbers, I'm going to get something larger, right? Or further away from the x-axis, if you think about it that way. But that's pretty straightforward. All right? In fact, can I do this right quick? Can we not put this as a separate rule? What do you think the next one is? If minus. So put 2 and put these in parentheses, because we can go ahead and put f plus or minus g. Right? Because if I'm subtracting 2 continuous functions, oh, let's pause. How sloppy of me. What is a continuous function? Continuous on its domain. Okay, why would that make it obvious that we need to specify that we're talking about at x equals c at some particular point? That's correct. Okay. So one function may not be continuous everywhere the other one is, okay? And let's just say I added e to the x and the square root of x, okay? E to the x exists everywhere, right? So when I do a sum or difference of those 2 functions, I would get a result. In some intervals, I may or may not get contributions by both functions. Does that make sense? Okay. The next one, you could guess, even if your book's not open, is fg, f times g, right? This theorem, as all theorems do, is powerful in the sense that it keeps you from having to rethink that every time. If you understand the theorem, then that means you can say, because if it's a theorem, you can state, by the properties of continuous functions, this is a continuous function, okay? You just have to first specify the continuity of each of the functions involved, okay?
The rules that we learned in section 1. This is like the rules we learned in section 1.
Only in the sense that we're combining 2 functions, but not really any other way. But what they do all have in common, the properties of limits approaching c, and the properties of limits approaching either of the infinities, and these rules, is that they give you, what would they have in common? Let's see if I can get something out of y'all. What would they have in common? Okay, well here's what I'm getting at. You might not go to this rule first, and since we're kind of pressed for time, I'll go ahead and tell you what they have in common. They have in common that they verify what your intuition or common sense would have told you, right? So if you just said it before you had these theorems, oh well, this is continuous and this is continuous, they have to be continuous when you add them together. That has no authority to it. But if I can say by the properties of continuous functions, or I can say by the properties of limits, you see what I'm saying? I'm citing a property, or I'm demonstrating my knowledge of that property, then that's a more powerful statement. All right? 4, which is one that always sneaks up on us, is k times g. I'm going to rewrite this a little different from the way the book did. K is any number. And then there's one more that you should write underneath, but I have not left myself room on this screen, and that is Rule 5. Now this one you should be able to guess because it's the only one left. Quotient. We've done a sum, a difference, a product, a constant multiple, and the only thing left is a quotient, right? So this is the quotient. So F over G, and I paused for a reason. Yes. Provided... Well, actually, provided, now I'm going to write this and read it to you, but then I want you to tell me why. Provided G of C does not equal 0. Right, because we're only looking at x equals C, right? So G of C can't be 0. So when I plug 0 in, if I get 0, we've got it, this doesn't apply. Because that would create a discontinuity just like it always has in terms of thinking as a pre-cal student. All right? So you cool with that? Pretty straightforward? It is as straightforward as it looks. Some theorems are not. All right? We're going to jump right into our next theorem, which is related to Theorem 6. This is Theorem 7. This is the composite of continuous functions. And this one is much, much, much shorter. It's literally a sentence. Okay. Now, this one also seems a little awkward possibly, but bear with me and we'll talk about it if it doesn't make sense as we go. If F is continuous, it's a terrible S. I probably got some other terrible letters I didn't stop and correct, but okay. If F is continuous at C, that's not tricky, and G is continuous at F of C, and I'm going to pause because that's probably the part you're like, what? I'll pause at the appropriate moment here in a second. Then the composite now, in your book, they have the other notation, but I'm going to use the one that I prefer and that you told me last year you prefer. G of F of X is continuous at C. Then I'm going to hop down here and write in fairly large notation for our discussion G of F of X. All right, talk to me about what you think as far as the meaning of this, and if there's anything that bothers you, we need to talk about it. And I guess for it to bother you, you actually have to be thinking about what it says to make sure it makes sense, and that's what I'm asking you to do right now. Is there anybody for whom this does not seem obvious? Is there anyone for whom the F of C bit bothers you? Okay, there's a couple of honest hands. I think I saw 3 hands, and oddly enough, they were all female. No coincidence. All right. Not to be sexist, just to be observant. All right. And G is continuous at F of C. All right, well, why would F need to be continuous at C?
Because you find a point of
Because if I'm interested in continuity and F isn't continuous at the point, then we already have a problem, right? Okay, so because Well, let's back up. Yeah, okay. If f is continuous at c, all right? And then we have to be continuous. G has to be continuous at f of c. All right, well, if you don't understand this, I would ask you to consider, and maybe I'll hop over here on another screen and do a little example right quick. Let's say that f of x equals x plus 2, and g of x equals 5 minus x. Find f of g of 1. Do that now. Find f of g of 1. What's the very first thing you started doing when I asked you to do that? What's the very first step? You're sounding like those insane monks again.
Plug 1 into G.
You would plug 1 into G. Why? Because we learned in 6th, 7th grade, somewhere in there, you always start at the innermost part of a thing, right? Whatever the task is, PEMDAS tells you to start inside, right? So if I start inside, I have to find G of 1, right? Well, what if G of 1 gave me a non-real result? Like let's say when I plug 1 in, I got 1 over 0. Is that okay? Doesn't that just sort of break down the machine? So now let's go back and look at that wording. So we're talking about this second part, and G is continuous at f of c. Now do you see why? Because the f of c in this case is the inside part, right? Because we had G as our outside function. So the f of whatever I'm plugging in has to give me a real result in order to find this composite, right? So I can't even talk about continuity if either of those is undefined there. Does that make sense? Okay. Does that clear it up for the hands that went up? And for the ones that didn't go up? That should have gone up? All right. I have really got to clean this screen. It's kind of nasty. All right. I'm so excited to say that we have one more little bit, although this is a pretty huge bit. Theorem 8. All right. And this is the intermediate what does intermediate mean? Between. The intermediate value theorem.
It means you run the 400.
That's the intermediate distance, isn't it? As opposed to short versus long. All right, the intermediate value theorem for continuous functions. I'm trying to decide if I have room to write that in case you're wondering why I'm stopping. All right, and I'm going to abbreviate both continuous and function so that we can actually talk about the the theorem. The intermediate value theorem for continuous functions. We do not want to have to say that every time we refer to it, do we? Thank God there is a universal definition. We will, and so will every other mathematician on the planet, give or take the language they're speaking. We call this the IVT. And you too will call it the IVT. Yes. And notice that it's still on the wall. Now you see when we're covering this, right? Does that tell you anything? It's still on the wall because we use it throughout the year. Because when new words go on the wall, I take old words that we don't use that often down so that I have room to put the new ones up. And you see that one's still there. So other than the insane busyness that is my life, that's the reason, one of the reasons I leave it up there, to help you see, the importance of some of what we're learning in the early days. Because if it's still up there, that's your sign. All right, so I'm going to have you draw the picture first so that if we run out of time, I'm going to ask you to go back and copy the wording of it into your notes later, because I want to explain this picture to you, and maybe it's just because I have a very visual way of processing information, but for me, it's the pictures that tell me what I want to know. All right? So, we are looking at, in this picture, an interval from A to B, all right? And this is the x and y axes, as you would presume it would be based on the way I drew it, but just for emphasis, I will say that. All right? And let's say we have some function. The only thing I'm deciding now is what color to make it, so let's make it white, just because it'll jump right off that green board, all right? And I'll try to make it look somewhat like what you see in your book. All right, so I have this function, and this is my y equals f of x. Well, now I'm going to come back and draw in the little dashed lines, but I'll tell you what, before I do that, let's talk about this function. All right, at the left endpoint, which I will come back to my white so that I can mark on it. All right, at the left endpoint, what would the coordinates of that point be if that is where, and I'm jumping back and forth between colors here to color code this, if that is the location of A. And on the opposite end, that's our B. Okay? What would the coordinates of my left endpoint be in terms of that notation? Right. So at that location, the left endpoint, my point would be A, f of A, and my right endpoint would be B, f of B, right? Okay. Well, then if I'm at A, f of A, and B, f of B, when I draw, and I'll back out of the way so I don't block anybody's view, or try not to. All right, when I draw a little dashed line horizontally, that tells me that the y-coordinate here is f of A, right? Okay, and then if I draw a dashed line across the top, that one's not as pretty. Let me see if I can make it a little better. Then this one would be f of B. Does that make sense? Well, we're going to come back and toss a C somewhere between A and B. Okay? And there's that C we've been talking about all day. And I'm going to draw my little dash line up to the line. Again, what would that give me if I come back here? That gives me f of C. Relate A, C, and B as x values to me. What's the biggest x value here? No, the biggest x value is B, right? And the biggest, or I'm sorry, and the smallest is A. And where is C? Somewhere in there. It's intermediate. C is the intermediate value. Okay? You see where we're going with this? All right, now, well, look what happened when I traced those lines back to the y-axis for our reference points there. Now relate f of A, f of B, and f of C to me. That is correct. Okay? So what this tells you, now I'm going to read it to you, and then I think, no, we'll actually try to write it. I don't know if I'll be able to because I'm kind of slow with this thing sometimes, but we'll try it. Okay? So now, that picture makes sense to you? All right? Then, and I'm going to use my abbreviations and whatnot, so if you need clarity, you can come back and compare this to what the book says. But a function, FCN, y equals f of x. And I will sit back on my stool so y'all can see from that corner over there. A function, y equals f of x, that is continuous. And again, I'm going to abbreviate continuous to CONT period. On a closed, well, in fact, I'm not going to say on a closed interval. I'm going to write this. And if it's not obvious to you, maybe you should come back and copy the wording. Because bracket A, comma B, bracket is in fact a closed interval from A to B, yes. Takes on every value between f of A and f of B. Period. In other words, I'm going to read this second sentence to you, but I don't necessarily think you need it to understand this theorem, and I care less that you could recite the theorem than that you can apply it, okay? Because I want to talk about it for a minute before we go. The second sentence says, in other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c value between a and b. All right? Well, this only talks about the betweenness. What part of this picture gets left out of the conversation? No. C is in the conversation, because what are we assured by the picture and the statement in this theorem? We are assured that if I pick an x value between the endpoint values for that interval, so if I choose any number in that interval, and the function that I'm looking at on that interval is continuous, and I just need that interval to be continuous. It can be a function that's not necessarily continuous outside this interval, but if it is continuous on this interval, then if I choose any x value between a and b, when I plug it in, this theorem promises me that somewhere on that interval there is a value that's going to be between f of a and f of c. In other words, every value, and there's an infinite number of them there, right? Every one of those values is an output of that function on that interval. So if my interval is from 1 to 3, and let's just say, let's see if this helps you at all. All right, so let's say, and I'm going to switch colors to remind you that this is not part of the theorem, this is just some thinking on paper. So let's say f of 1 is 5, and f of 3 is 8. Okay? And that's sort of like what this picture looks like, just so in terms of the relationship between them. But notice this theorem doesn't say the function's increasing, it doesn't say it's decreasing, it doesn't say it's a polynomial. Any continuous function this is true for, okay? So what this promises me is that any value I pick between 1 and 3 has to give me a value between 5 and 8. No, that's not a good way to say that. Because I'm not assured, because what the function could do, let me show you what I'm talking about. If I had the ability to do this without making that mark on there. All right, so let's say I have this function. And here's my b, and here's my a. And let's say the function does this on that interval. All right? Well, the intermediate, and let's just say that, well, if I'm going with this picture, then my f of a would be somewhere like right in there, right? Okay? And my f of b would be somewhere like right in there. Now, if I'm only going to get, what I get from this theorem is the promise that every value between there and there is going to occur for this function, okay, in that interval. Now, it also, because all the values there are covered, aren't they? Even though we get this big dip that falls out of the range, it says that the output is going, every output between this output and this output is going to happen somewhere in that little box that's created by that. It doesn't say it's not going to leave the box because you're getting other values, but you're not going to skip any, okay? And I will tell you where, and I think this is where they start with the work in this chapter, and I don't know that there's that much practice, but what's typically going to happen, if I had, let's say I had f of 1 equals -5, and f of, and this is going to tell me who understands everything I just said, no pressure, f of 8 is 7. Tell me something you know for a fact. And tell me an output you know for a fact that f has between x equals 1 and x equals 8. 0. Why? Because if I'm dealing with a continuous function on this closed interval, and the left endpoint is a negative output, and the right endpoint is a positive output, somewhere in there, we cross the x-axis how many times? What can you say mathematically? At least once. Right? Could be 3 or 4 times. It's kind of like that psycho function we looked at the other day. The closer we zoomed in, the worse it got. So there's no way we could have predicted that from the original picture, though, right? But there's no rule here that doesn't say it doesn't happen more than once. It just guarantees you that you're going to get that output somewhere on the interval. Does that make sense? Okay. Awesome. That is the end of the lesson, and I want you to continue working on 2-3 after I finish, and don't start talking because I have a hand up. I want you to continue working on 2-3, and then we'll start tomorrow with any questions you have. That'll be a good way to close out the Friday. We will close out 2-3 tomorrow. Yes?
So
Why wouldn't it?
Like, because if it's the same values, it wouldn't be.
Yeah, okay, but listen, what if my, did y'all hear his question? It's a very astute question. He said, so this wouldn't apply to what's true about a horizontal line? The output is the same everywhere, okay? So what's between 4 and 4? There's nothing, right? There's only 4, right? So if I get 4 here and I get 4 there, the intermediate value theorem doesn't tell me much. And if I don't know it's a horizontal line, then we got a problem, right? Because, well, I'll tell you, the intermediate value theorem doesn't assure me anything without knowing more about what's happening in between. Does that make sense? We have other stuff we'll talk about with respect to that very situation, though. Very good question.